Hello and welcome to this lecture. This lecture is going to be on conditional densities. Okay, once again we've been doing this continuous random variables, going through all the different types of densities, trying to make sure we have the skills of manipulating these densities carefully. We saw joint density, then we saw the marginal densities. Now we are going to see, we also saw the independence property, and now we are going to see conditional densities. Okay, so this is sort of very similar to what we did with PMFs in the discrete case. We are doing the same thing in the continuous case with densities. Okay, so here's the definition. The definition is, there's lots of writing, but important point is this. This is the important point. You have to fix an A for which the marginal is greater than 0. Okay, so you take a value for x so that the marginal density of capital X at A ends up being positive. Once it's positive, you can define this conditional density. What is this conditional density? This is the density of y, conditional density of y, given that x equals A. Okay, so I'm not going to go into great detail on where this comes from. Many of you may get confused by this x equal to A. Why is this confusing? Because x is a continuous random variable and the probability that x equals A is usually 0. Okay, so what is the meaning of conditioning on an event of 0 probability? Okay, so again you have to sort of liberalize and think that when I say x equal to A, I really mean x around A, and sort of in the limit I am getting something, and this is a good enough density. It's a valid density and it works. Okay, so don't worry too much about where this comes from, but this is just a definition. Okay, the conditional density of y given x equal to A is simply the slice. So notice this one, this is the slice, right? This is the slice of joint at x equal to A, except that you are normalizing it, you are dividing by this fx of A. Okay, so this is what makes it a density. Okay, so fxy of A comma y will just be a slice, it will be just one function of y. You divide by the marginal, this makes it a density. Okay, so why is this a density? It is actually very easy to check, right? So what is fx of A? Fx of A is actually integral minus infinity to infinity fxy of A comma y dy, isn't it? It's just this slice integrated from minus infinity to infinity is the marginal. So now I have divided it by this. Okay, so if what does this mean? So if you actually do the integral of fy given x equal to A of y from minus infinity to infinity, you will simply get 1. Okay, so you notice how this one has to happen, right? Because the denominator is simply the integral of the numerator from minus infinity to infinity. Okay, I am normalizing by that. So if I integrate again, these two will cancel and you will get 1. Okay, so it's a very simple trick to get a density, and that density is called a conditional density. Okay, there are so many densities to work with. This is joint density in 2 dimensions. Then you had these marginal densities. Okay, now I have a conditional density also. The same thing, whatever you did for x, you can do for y. You fix a b such that fy of b is greater than 0 and take a slice on y, then divide by the marginal of y. Okay, so in many problems people get mixed up with x and y and this notation. This notation is also, I think, slightly more laborious, confusing notation. There's no way to avoid it. You have to be very precise when you write it down. Okay, so as you get more practice, this will be clearer, but this is the definition of a conditional density. Okay, there are lots of conditional densities. Okay, quick look of properties. These are both valid densities. Okay, so you can think of conditional random variables, continuous random variables, y given x equal to A, x given y equal to B. These are the random variables with those densities, right? So they're all related and they have that. Okay, so this is the important formula here. So basically what is the meaning of times here? So I mean marginal times conditional multiplied by conditional. Okay, joint density is marginal density multiplied by conditional density. Okay, so whenever you have this being true, this is something that you can write down. Okay, so when you have the marginal densities being non-zero at the point, you get this. Okay, so when you write it down, you can write this wonderful little formula. Okay, so the joint density fxy of A comma B is the marginal at A multiplied by the conditional y given x equal to A at B. You can also take the marginal density of y and then multiply by the conditional density of x given y. So you see how these properties which were satisfied by probability, right? So, this is sort of like the intersection property, right? Probability that x equal to a comma y equal to b, right? X equal to a and y equal to b, right? That factors as probability of x equal to a times the conditional probability of y equals b given x equal to a. So, these results are like similar results, but in terms of density and not probabilities. In the discrete case, you had probabilities and all these results were true. In the continuous case, these results are true for densities, the conditional density, marginal density and the joint density. Okay. So, people write this as this formula. This is a very comfortable formula to keep in mind. Okay. So, this is just quick properties of conditional densities for you. Okay. So, let us see examples. I have put down a few examples here. So, uniform on unit square, let us go to that. So, this is the support, just drawing it in a big way. This is the support. So, if you fix x equal to a, what is the conditional density going to be? Okay. So, we know that the marginal is 1 again. So, the conditional density will again be uniform, right? Y given x equal to a for every a will be uniform, right? Do you see that? It's you can go through the calculation, but you know just the picture tells you the story, right? So, every x equal to a, y is also going to be uniform. The same thing with x given y equals b. This is for of course a between 0 and 1, b between 0 and 1. This is also going to be uniform 0 comma 1. Okay, so this is the first one. This is uniform on unit square. Let's do the second one. The second one will be a little bit more interesting. Oops, let's draw it a little bit better. Okay, so this is my support, right? Half 0. So this is my support. Again, you can quite easily guess this y given x equal to a. Okay, so remember this has to be a density now, right? So a particular a. So if you fix a here, a between 0 and half, y given x equal to a. Remember that slice, it's constant between 0 and a half. What will the density be? The density is going to be uniform 0 to half, isn't it? You can calculate it, you will get that. Okay. So also from the picture, it's quite easy to see this. Now, if a were to be between half and 1, you will get uniform half comma 1, right? On the support you can see it's going to be uniform. Okay, similar case you can make for x given y equals b. I'm not going to write it down. Okay, so you can see for y equal to b, so for y b between 0 and a half, x given y equal to b will be uniform 0 and half. If it goes to half to 1, it will be uniform half comma 1. Okay. So, you see the conditional densities, how they work out. It's just basically the conditionals and marginals are slices done differently. So, when you do marginal, when you do the marginalization with respect to x, at every slice you integrate and you find the total marginal probability. You are only worried about the distribution over x. So, here you fix an x and your distribution, you are worried about the distribution of y given x takes that particular value. So, as x goes differently, you will get different densities for y. Those are the conditional densities. Okay, hopefully you see the minor distinction here. So, here are more examples just to get you practice here. So, this again the same examples, I am just going through them a bit fast here, 1, 3, 4. So, you can do this. This is one example, this is the next example which we had 0, 1, 0, 1 and then 1, 2, 0, 2, right. So, this is the other example we had. Okay, and then the third example we had was this. Okay, so third example is maybe a little bit interesting. So, let me spend some time on that. This 2, 2. Okay, so this one again, y given x equals a. So, you can make a slice here. So, it's just uniform and flat, right. So, the flat density is just going to correspond to a uniform 0, 4 distribution. Right, and this is between, sorry, a between 1 and 3. So, x given y equals b. So, if you do a slice like this, this is again going to be uniform 1 comma 3 and b is between 0 and 4, isn't it easy enough to see. So, here things are going to be slightly different. You can take a here and here if you like, and you will see I will just do the conditional of y x equals a between 0 and 1 is going to be uniform 0 1. Okay. So, y given x equal to a between 1 and 2 is uniform 0 2. Okay. So, you can see that is how it is. Okay. So, it is all flat and same. So, in this case notice what happens if you put a here, this is x plus y equals 2. So, this point is going to be 2 minus a, isn't it. So, if you look at this slice, when you want to do y given x equals a, okay, a between 0 and 2, this is actually uniform, maybe I should write it down carefully. This is uniform in the interval 0 comma 2 minus a. Okay. Notice how the a shows up here in the distribution. Okay. So, y given x minus x equals a is actually uniform from 0 to 1 minus a. So, if you write down the conditional density of y, it is going to be 1 by 2 minus a for y between 0 and 2 minus a and 0 else. Okay. So, notice how, I mean it is quite easy still, you just have to look at the density carefully, but it is still uniform, right. So, at every a it is uniform, it stays flat. So, the density is uniform, even if to normalize it goes uniform, but the width of the density keeps changing with a. Okay. As a goes from 0 to 2, the width goes from 2 to 0. You can sort of see it from this picture, right. For every x, y has a different distribution, it is uniform between 0 and 2 minus a. Okay. So, I believe the next problem I am doing is for a non-uniform distribution. Again, we have seen this before, we have seen the conditional density, right. So, the conditional density for this guy is, so the conditional density is just integral y from 0 to 1 x plus y dy. Okay. So, you remember this calculation, it was just x y plus y squared by 2, you plug it in between 0 and 1. So, you are going to get x plus half. Okay. So, this is going to be the marginal. If you do the marginal of y, you will again get y plus half, x between 0 and 1, y between 0 and 1. Okay. So, we saw before how this is a valid density and all that. Okay. So, now what is going to be f y given x equal to a of y, and a, I mean a we can pick between 0 and 1, right. The marginal is non-zero. This is going to be the joint density, which is x plus y, divided by, well, x is a, right. So, it is a plus y divided by fx of a. So, it is a plus half. Okay. So, this is the density, it is a plus y divided by a plus half, and what is the range of values of y? Y goes from 0 to 1, isn't it? Does this make sense? So, let us try and sketch this. So, this is a bit interesting, isn't it? So, if you look at y here and you sketch f y given x equal to a of y, at y equals 0, it is going to be a by a plus half, and it is a linear function, it goes from 0 to 1. At 1, it is going to become a plus 1 by a plus half. Okay. So, it is some function like this, this is how it looks. Okay. So, this is the marginal density. So, if you actually look at the slice of this x plus y, this is how the marginal is going to look. Okay. So, you can check whether this is a valid density or not. For every a, this needs to be a valid density, right. So, here you will have a by a plus half as the area here, and this area, if you actually work it out, it will be half into this height. What is this height? It is a plus 1 minus this. So, it is going to be 1 by a plus half. Okay, so it's if you add, so it's going to be half by a plus half, right? So this area is going to be half by a plus half. This area is going to be a by a plus half, and you add it up, you'll get 1. Okay, so this will be a valid density. So notice how this sort of pictures the slice, the conditional slices, right? For every a, how does y look? Okay, remember I told you the support is 0, 1, but it was sort of an uneven shape, right? It's not a non-uniform shape, some sloping angle from 0, 0 to 2, 2 and 1, 1, etc. So it's a different sort of picture. But if you slice it at x, y is going to look like this. It will look like this. Okay, so because at x equal to a, it starts at a, no? It starts at a and goes up. So it will have a picture like this. Okay, so this is the conditional density. So just by basic integration, finding the marginals and looking at the structure carefully, you can do the conditionals as well. Okay, so hopefully you got a reasonable idea. I know this last few lectures were a lot about this integration and working with conditionals, marginals, etc. This will need some practice. Hopefully you can do the assignment questions, activity questions and all that and pick up some practice, etc. And this basic skill is important. For simple functions like this, you should be able to understand the support and understand the conditional, understand the marginal, do some quick calculations and find out what they are. These are very basic skills and you should have them. Okay, thank you very much.